Okay, so we were talking about working with these fractions, and we saw that 3/4 plus 1/5 couldn't be done because they have different names. So we need to look at ways to rename fractions. So let's go back up to our illustration here, and let's try to rename this fraction. The simplest way to do that would be to take each of these pieces of pizza and cut them into 3 equal pieces. So now that originally was 3/4, how many slices, how many pieces does it take now to make a whole object? 12 of them. There were 4, each got cut into 3. Now there's 12. How many pieces do we have? 9. Very good. We had 3. Each of them got cut into 3. Now we have 9. Do we have any more or less than we did before? No. 9/12 and 3/4 are exactly the same amount. They just look different. The reason that they're the same is because of what we did right here. We multiplied by 3 over 3. 3 over 3 is just 1. We multiplied by 1. So we can't change the value when you multiply by 1. We can only change the appearance. That's a tool that gets used a lot in math for other things as well. When we get to our measurement conversions, multiplying by 1 like that, it's called the unity fraction, is how we do a lot of our measurement conversions as well. So we can multiply the top and bottom of a fraction by the same number. It'll change the appearance, it'll change its name, but it won't change its value. So if I have 2/5 and I want to change it into 20ths, I have to first figure out what do I need to multiply the 5 by to turn it into a 20? What is it? 4. Good. So that means I have to multiply the numerator, the top, by the same thing, times 4. So 2 times 4 is 8. 8/20 has the exact same value as 2/5. It just now has a different denominator, different name. We can go the other direction as well. We might have 18/30. Well, if I can multiply the top and bottom by the same thing, I can reverse that process. I can divide the top and bottom by the same thing. What can both 18 and 30 be divided by? Okay, 6. Now, some of you may not have seen 6. I heard somebody whisper 2. 2 would be fine. 3 would be fine. We've always been told you've got to find the largest number that goes into both of them. It's not true. Any number that goes into both of them will work. You may just have to repeat the process until you're done. 18 divided by 6 is 3. 30 divided by 6 is 5. That's 3/5. Another way of renaming our fractions that we may run into might look like this. 45/7. The 7 is telling us it takes 7 pieces to make a whole object. We have 45 of them, which means we have more than enough pieces to make a whole object. In fact, we can make several of them. How can we figure out how many whole objects we can make? Well, if we did 45 divided by 7, what's that going to be? Something like 6.428574143 approximately. Divide that out. Don't worry, it's not contagious. Math, the calculations in math are about patterns. And once you start to see what the patterns are, doing the calculations is actually very easy. There's patterns everywhere in math. And that's just one of them when you're dividing by 7. There's a distinct pattern that comes up that you can repeat. So anyway, what's that telling us here? Well, it's telling us we can get 6. Go ahead.
It's improper.
Yeah, it's improper. We can get 6 whole objects out of that. And there's some pieces left over. So now we need to figure out how many of those pieces are left over. how many of those sevenths are still there after we take out 6 whole objects? Well, we took out 6 objects with 7 pieces. 6 times 7 is 42. So how many are left out of our 45? 3. Very good. It's basically a division and a remainder. Taking 45 divided by 7. 7 goes into 45 6 times. 6 times 7 is 42. There's 3 left over. So those 3, the remainder of 3 is still in our fraction. Still the pieces left over. This is what we call, as you said, an improper fraction. Now the word improper fraction implies there's something wrong with it. There's nothing wrong with it. We just don't like having it written that way because we've got it broken down into all these pieces. It's usually easier for us to see it as whole numbers, whole objects, and then leftover pieces, which is right here. This is what we call a mixed number, because it mixes whole numbers and fractions together. You're fine with the broken pieces? Well, in fact, there are times when we prefer to have it as the improper fraction. So let's say we have 28 fifths. So we're going to do the same thing. 28 divided by 5 is 5. 5 times 25. 5 times 5 is 25, so there are 3 pieces left over. So 5 and 3/5. Sometimes, as we said, it's beneficial to go the other way. Take that mixed number and turn it back into an improper fraction. So we need to take this 5 whole objects and break it back into pieces. How do we know how many pieces? Well, we use the denominator tells us how many pieces. This isn't the greatest example, but we're going to take our whole number times our denominator. 5 times 5 is 25. And add that to our pieces that are already there, the numerator. 3 times 25 is 28. That gets us back to 28 fifths. So if I have 7 2/3, what are we going to do?
7 times 3.
Perfect. 7 times 3 is 21. Add that to the 2. 23/3. Perfect. So now we can rename our fractions. Let's go back to 3/4 plus 1/5. And I'm actually going to write it out like this. I'm used to doing addition vertically. It just works easier for me. We have to rename those to give them the same name. Well, the first step we have to do is figure out what name that's going to be. There are actually several different methods. One is to make lists. You know, we know that 5s, if you count up by 5s, it's going to be 5, 10, 15, 20, 25, 30, so on, right? So we know what those are going to look like. So let's count up by 4s. It'd be 4, 8, 12, 16, 20. There's our first match. So that would be our smallest common denominator, or least common denominator. Another way you could do it is just multiply them together. 4 times 5 is 20. That will not always give you the smallest one, but it will give you a common denominator. And before we're done here, we'll look at an example where we do that. So our common denominator here is going to be 20. What do I have to do to the 4 to make it a 20? Times 5. So I have to do 3 times 5, which is 15. Good. What's going to go here? 4. Good. 5 times 4 to make 20. 1 times 4 is 4. So 15 plus 4 is 19. And we keep the same name when we add. So 19 20s. Now, I'm not going to mess around with simple fractions too much. We're going to jump into mixed numbers here. So let's say I have 13 3/4 plus 9 5/6. We still need common denominators, so we have to change those fractions. What's my least common denominator between 4 and 6? 12. Very good. What's going to go here? 9. 4 times 3, so 3 times 3 makes 9. What's going to go here? 10. 6 times 2 is 12, so 5 times 2 is 10. So now you can see that fraction is just lined up at the end of the number, kind of like it's the last digit of the number. And that's exactly what it is. The fraction is nothing more than the last digit of the number. Just like any other addition, we're going to start on the right and work our way back to the left. 9 twelfths and 10 twelfths. We add the counts. 9 and 10 is 19. We keep the same name of twelfths. Now that's improper. We can split that up into, how many times can we take 12 out of 19? Once, with how much left over? 7 twelfths. So just like with any other number, we're going to keep part of it. We're going to keep the fraction part here, 7 twelfths, and we're going to carry part of it. We're going to carry the 1. So 1 and 3 is 4 plus 9, 13. Carry the 1. 1 and 2 is 2. It's 23 and 7 twelfths. What if you'd have looked at this and said, okay, 4 times 6 is 24? Would it work? Yes, it would. It's just this would be 18 24ths and this would be 20 24ths. When you add them, you get 38 24ths, which is 1 and 14 24ths. Well, that 14 24ths reduces to 7 twelfths. So you see, you're going to end up with the same result, just have an extra step of having to reduce it somewhere during the rest of the process. Let's look at subtraction. Need a common denominator. What's it going to be here? 20. Very good. What's going to go here? 5, and here? 4. Good. So again, just like addition, we start on the right, work our way back to the left. That fraction is just the last digit of our number. 5 twentieths minus 4 twentieths is 1 20th. 9 minus 3 is 6. It doesn't stay that easy. We could only hope, right? So something like this. Now, you might be noticing that I rewrite the whole number too when I rename my fractions with mixed numbers. A lot of people just rewrite the fraction. I always rewrite the whole number so that it stays with it. For some reason, it's confusing to me if I separate them out. If that's how you do it and it works, that's fine. What's my common denominator going to be? 24. What's this going to be? 8 and 9. So here we go to subtract. 8 minus 9 can't be done. So we're going to have to borrow from the 8 and make it a 7. What happens here? Yeah, we have to add 24 to it. We borrowed one whole object, but that has to be broken into pieces. The denominator tells us how many pieces it breaks into. So 24 plus 8 is 32 24ths. 32 minus 9 is 23 24ths. 7 minus 6 is 1. Multiplying. 3/4 times 2/5. As we saw up above, when we multiply fractions, we just multiply straight across. 3 times 2 is 6. 4 times 5 is 20. What can we still do with that? Reduce by 2. Gives us 3/10, 3/10. Some of you might have been looking at this original problem wondering, why didn't he cross cancel or cross multiply? Some of you might be wondering, what's cross canceling? Well, we see that we're going to have 3 times 2 on top and 4 times 5 on bottom. Excuse me. You might notice that both the 4 and the 2 can be divided by 2. So what I can do is I can actually divide that out before I multiply. 4 divided by 2 is 2. 2 divided by 2 is 1. So 3 times 1 is 3. 2 times 5 is 10. We basically reduced before we multiplied. Now in a problem like this, it's about the same amount of effort either way. But we can run into problems like this one. Where we could do 24 times 35, which is what, 840, and 25 times 36, which is 900. And we could reduce that. Now, typically, you'd have to look at it, probably divide by 10, because they both end in zeros, and then they're both even still, so divide by 2, and so on. I'm just going to assume you guys look at that, and you both all see that they can both be divided by 60. Easily, yeah. It just pops right out at you, right? So it reduces. I mean, you would get there. Like I said, most of the time I would divide by 10, so now you got 84 over 90. Well, they're still even, so I divide by 2. You got 42 over 45. Might take you a while there to see that they're both divisible by 3, which gets you to 14 over 15. Or you could have seen 24 and 36 can both be divided by 6 works. If I divide by 6, 24 divided by 6 is 4. 36 divided by 6 is 6. Okay, somebody said 12. Yep, you can divide by 2 again to get 2 and 3. Or you could have divided by 12 first and get the 2 and 3. You can see again, you don't have to find the biggest number right away. You can go in steps if you want to. 25 and 35 can both be divided by 5. 25 divided by 5. 5. 35 divided by 5. Careful. 7. There you go. I know, it's Friday. There's 2 times 7 is 14, and 5 times 3 is 15. So we get there with the reduced answer. And to me, it's easier to reduce before I multiply. Now, I'm not going to waste any time on simple fractions multiplying. We're jumping right into mixed numbers. Let's do something like 4 1/3 times 7 2/5. Multiplying mixed numbers is actually an extremely difficult process. In fact, if we went to any university and found 10 math majors, asked them how to multiply mixed numbers, I would actually be surprised if even one of them could show you the right way to do it. So my question to you is, how do we do it? Obviously, we're going to multiply them. How do we make it work if it's such a difficult thing? Well, we're going to cheat. We're not going to multiply the mixed numbers. We're going to change them into improper fractions. So 4 1/3 becomes how many thirds? 13, good. 4 times 3 is 12, plus 1 is 13. 7 2/5 becomes how many fifths? Perfect. 7 times 5 is 35, plus 2 is 37. Now at this point, because these are fractions, we could cross cancel if there was anything that divided out. Unfortunately, there is not. So we have 13 times 37, which is, I'm actually pretty sure to calculator for that one. It's Friday for me too. 481, and 3 times 5, which is 15. So now again, if you're looking at that and you don't see that that's 32 and 1/15, we can do the long division with remainder. 481 divided by 15. 15 does not go into 4, so leave that blank. 15 goes into 48 3 times. 3 times 15 is 45. 8 minus 5 is 3. Bring down the 1. 15 goes into 31 twice. That's 30. With 1 left over. So that is 32 and 1/15. Anybody curious as to how you'd actually multiply the mixed numbers? Yeah? Okay, let's do it. Why not? Don't write this down unless you really, really want to. I will never ask you to do this. This is kind of based on, like, if we have 32 times 43. Not only do you have to do the 3 times 2, but you also have to do 3 times 3. The same is true here. We have to do the 2/5 times 1/3, which is 2/15. But we also have to do 2/5 times 4. How do I multiply a fraction times a whole number? Yeah. I make it 4 over 1 to make it a fraction. So now 2 times 4 is 8. 5 times 1 is 5. 8/5 or 1 3/5. So now the 2/5 is multiplied both digits in the top number. I move to the 7. 7 times 1/3. Again, 7 over 1 times 1 over 3 is 7 over 3 or 2 1/3. And 7 times 4 is 28. Well, now I have to combine this mess here. First, I have to find common denominator, which looks like it's going to be the 15, so this will stay 2/15. This is going to be the 1, and that 3/15 or 3/5 becomes 9/15. We have the 2. 1/3 is 5/15, then just 28. So we got 2 plus 9 is 11, plus 5 is 16/15, which is 1 1/15. So we'll keep the 1/15 and carry the 1. 1 1 is 2, plus 2 is 4, plus 8 is 12, so that's 2 carry the 1. We get 32 1/15, just like we did before. I don't know about you, but that was kind of exhausting to me. So I think I'm going to stick with changing them to improper fractions and multiplying. Let's do one more example of that before we move on to division. So let's do 3 1/8 times 2 4/5. Tell me what to do. Okay, 25/8. Good. 3 times 8 is 24, plus 1 is 25. 14/5. 2 times 5 is 10, plus 4 is 14/5. Now what? Yep, we can. Yeah, so what can we cross out?
5 and 25.
5 and 25 divided by 5. Good. 5 divided by 5 is 1. 25 divided by 5 is 5. That's okay. I know what you were thinking. So you got 5 and 1. Can we cross out anything else? 8 and 14 both divide by 2 to give me 4 and 7. So now 5 times 7 is 35. 4 times 1 is 4, which if you divide it out, it is 8 3/4. Not so bad? Okay. Let's look at division. We said that division follows the same rules as multiplication. When we multiplied, we multiplied straight across. So does that mean I can divide straight across? Can I do 12 divided by 4 is 3? 25 divided by 5 is 5? I hear a bunch of people saying no. Is that the correct answer? It is. Will it work every time? Yeah. So why don't we do it that way? Well, because we run into things like this. 3/4 divided by 2/3, that's not going to work out. 3 divided by 2 is 1.5. 4 divided by 3 is 1.33333, or 1 1/3. It doesn't work out nice and even like this one did. What were we taught to do with this? Multiply by the reciprocal. Good. The 3/4, the first number never changes. But instead of dividing by 2/3, we multiply by the reciprocal of 2/3. Reciprocal is just flipping the number over, exchanging the numerator and denominator. It'll be 3/2. And now, 3 times 3 is 9. 4 times 2 is 8. 9/8, of course, reduces to 1 1/8. Believe it or not, this process, multiplying by reciprocal, comes from that. Let me show you how. Again, you don't need to write this down. I won't make you repeat it, but it's a little bit of math history that's kind of interesting. Once upon a time, if I had 3/4 divided by 2/3, what we would have done is we would have looked at this number we're dividing by, the fraction we're dividing by. First of all, we'd make sure it's reduced, and it is. 2/3 can't be reduced anymore. Then we would multiply the numerator times the denominator. 2 times 3 is 6. So we're going to use that 6 to rename this first fraction. So 3 times 6 is 18. 4 times 6 is 24. 18 24ths and 3/4 are the same number. They just look different. I've just renamed it. Now, 18 divided by 2 is 9. 24 divided by 3 is 8. 9/8, so 1 1/8. How on earth did we get from this to multiplying by reciprocal? It's not as big of a leap as you might think. You look at this piece here. 3/4 times the 6/6 divided by the 2/3. At some point along the way, somebody looked at this and said, hey, if I cheat just a little bit and I divide first here, 6 divided by 2 is 3. 6 divided by 3 is 2. What I get there is always going to be this fraction flipped over. Then all that's left is to multiply. So they came up with that name reciprocal, and they called this a reciprocal. And then they defined division to be multiplying by reciprocal so that they could skip these steps here. So like I said before, most of what we've been taught in math is a shortcut of the real process. Division is the one process that has been altered and changed the absolute most, to the point where you don't even recognize it anymore. Again, I'm not trying to change the way you divide fractions. I'm just trying to show you a little background. Let's jump up to doing like 5 1/2 divided by 3 1/3. Now for mixed numbers, since we're going to change it into multiplication, it makes sense that we do the same thing we do with multiplication. Make them into improper. 5 1/2 becomes 11 halves, 11/2. 3 1/3, 10/3. Good. Can I cross cancel the 2 and the 10? Say no.
Oh, no.
Why not? Well, because I told you to say that, right? Because it's division right now. We can only cross cancel multiplication. So now the 11 halves is not going to change. 11/2 stays the same. It's the number we're dividing by. The division always goes with the number after it. So it's going to be times 3/10. Now at this point, we could cross cancel if anything did. Unfortunately, right now, nothing is going to cancel. So we'll just multiply. 11 times 3. Did right for some reason today. 33. 2 times 10 is 20. We'll break that down into 1 and 13/20. Not so terrible?
No.
Better than a sharp stick in the eye?
Yes.
A little bit better?
A lot.
Okay. I had a student last semester ask me, well, how deep are you going to push it? Wow. Okay, so We are going to skip doing decimals because I'm going to assume you guys can do decimals. We will come back at some point if we get a little bit of time and maybe look at converting fractions to decimals. But decimals, I'm going to leave it out there for you guys to, like I said, I might pull up one of my other videos and put it out there for you to watch if you need a refresher on decimals. Otherwise, if we don't get to it today, we can answer questions next week if people do have questions on it. But I do want to take a look at integers. Integers come from the whole numbers that we've talked about. Remember, our whole numbers are 1, 2, 3, 4, 5. Pretend those are evenly spaced. 6, 7, 8, 9, 10, so on. They're numbers with no fractions or decimals on them, counting up. Well, the integers include all of those whole numbers plus going in the opposite direction, the negatives. So an integer is a positive or negative number that has no decimal or fraction on it. So let's start out by representing the number 6. There are a couple of different ways to represent the number 6 on the number line. One of the simplest is just put a dot at 6. Now that's a great pictorial representation, but not a good working representation. If you're going to work with it, if you're going to work with a value, we tend to define it or represent it with something called a vector. Now a vector is just a really fancy word for arrow. So the vector for 6 starts at 0 and it goes to 6. It's just that arrow. Excuse me. With these vectors, we have something called absolute value. The absolute value is just the length of the vector. There's an alternative definition of absolute value out there that's the distance the number is from 0. It's the same thing. The length of the vector is how far it is from 0. Now let's define 6 plus 2. So I've got 6 there. I'm going to put a vector for 2 up here. The symbol, the plus symbol, the operator for addition, what it is telling us to do, the definition of addition, is to combine the vectors. So I'm going to take that vector for 2 and I'm going to move it to combine it with the 6. So now what it's created is a single long vector that goes from 0 up to 8. Well, we all knew that 6 plus 2 is 8. We didn't need a picture to show us that. But what if this isn't 6 plus 2? What if it is 6 plus a negative 2? Well, now, negative 2 looks like this. We're going to move that to combine it with the 6. There's our 6. And it looks like that. 6 plus negative 2, we end up at 4. 6 plus negative 2 is 4. Now, I don't draw out the number line every time I add with negative numbers, and I don't expect you to either. But I do keep that picture in the back of my mind. Kind of like this. If I were trying to do negative 27 plus 41, what I am picturing is this. Here's 0. Negative 27 goes in the negative direction. Positive 41 goes in the opposite direction, and it's longer. So I'm going to go past. 41 has a bigger absolute value than 27. It has a longer vector. So it means I go past 0. This picture tells me two things. One, that I end up on the positive side of the number line. So my answer is positive. 2, those vectors point in opposite directions. So the solution is the difference in the length of the vectors. So at 41 and 27, the difference is 14. So it's a positive 14 is that answer. Likewise, I might have negative 21 plus 12. So here's 0. I've got negative 21, goes like that. Positive 12 goes the opposite direction, but it's shorter. So I'm going to end up short of 0. So I'm on the negative side of 0. Tells me my answer is negative. But again, the vectors go in opposite directions, so it's the difference in their lengths. So 21 minus 12 is 9. It's a negative 9. You'll notice when I subtract the length of the vectors or subtract the opposite values, I always put the big one on top and just subtract. I'm just looking for the difference in their length. I might have negative 37 plus a negative 18. So here's 0. Here's negative 37. Negative 18 goes the same direction. So what this is telling me now, obviously I'm ending up on the negative side of 0. I got a negative answer. The vectors point in the same direction, so it's combining the lengths, or combining the opposite values, which is 55. It's a negative 55. Does that make sense? Okay. Subtraction is where things get a little confusing. So we're going to start out with 8 minus 3. And if we were to do an illustration for 8 minus 3, here's our vector for 8. We'd say, oh, we got to go like this to get back to 5, right? We know that 8 minus 3 is 5. But if we look at this picture here, that picture looks exactly like the picture for 8 plus negative 3. It is the picture for 8 plus negative 3. The reason for that is the definition of the operation of subtraction. Subtraction is not an operation. It's part of addition. Just like division with our fractions, we said the division symbol works with the fraction that comes after it. So that's the one that has the reciprocal. The subtraction symbol works with the number that comes after it. Subtracting 3, bless you. Subtract 3 really means add the opposite of 3. Well, the opposite of 3 is negative 3. So subtracting 3 means add negative 3. Subtraction was just an operation that was developed to limit the amount of negatives we have to work with. Well, if I'm subtracting positive numbers like 38 minus 27, I'm not going to change it. I'm going to leave it as subtraction because that's not a difficult subtraction to do. 38 minus 27 is 11. But when I throw one of the numbers in there, one or more of the numbers in there is negative, like negative 27 minus 18, now it gets confusing because one of the numbers is negative. So I'm going to change it over. What happens to the negative 27? Stays the same. Just like with dividing our fractions, the first fraction never changes. The first number here never changes. But subtracting 18 becomes adding negative 18, adding the opposite of 18. So now looking at my picture, here's 0, negative 27, negative 18. That's going to be a negative 45. Or, here's the tricky one, 32 minus a negative 23. Well, the 32 doesn't change. Minus a negative 23 means adding. The opposite of negative 23 is 23, or positive 23. So that just becomes an addition. It's 55. Or you might have negative 37 minus a negative 41. That's going to become the negative 37 doesn't change. Minus a negative 41 becomes plus 41 plus positive 41. Negative 37, positive 41. The 41 is slightly longer, so we end up on the positive side. It's positive 4. Let's look at multiplication. We looked at 5 times 3. We said that was 5 plus 5 plus 5. Repeated addition. So with that definition in mind, negative 5 times 3 is pretty simple to envision. That's just negative 5 plus negative 5 plus negative 5. Or negative 15. Not so bad. However, what if it's 5 times a negative 3? Can I take 5 and add it together negative 3 times? That doesn't make any sense, does it? But in multiplication, as long as we're just multiplying two numbers, we can switch the two numbers around. We can switch the order. It's called commutative. So I'm going to do negative 3 times 5. So there I'm taking the negative 3 and adding it to itself 5 times. So negative 3 plus negative 3 plus negative 3 plus negative 3. There's 5. Which adds up to, not everybody at once, negative 15. There we go. Okay, many of you are probably taught, and rightfully so. Obviously, if you're multiplying two positives, you're going to get a positive. But if you're multiplying one negative and one positive, you're going to get a negative. Multiplying a positive and a negative, you're going to get a negative. You might have been taught negative 5 times negative 3. I don't need the multiplication in there even. The parentheses indicate multiplication. Negative 5 times negative 3 is going to be positive 15, because you've been taught that a negative times a negative is a positive. The question there is why? I mean, I can't take negative 5 and add it to itself negative 3 times. I can't take negative 3 and add it to itself negative 5 times. The definition of multiplication breaks down here. It doesn't apply. So how can we multiply two things when the definition doesn't work? Well, this actually occurs in math more than you would think. What we do is we look for a pattern. We look at the things that we can do with the definition and look for a pattern. For example, we had negative 5 times 3 is negative 15. So let's stick with the negative 5, and we're going to change the 3 to 2. So we're going to reduce that by 1 to get 2. Negative 5 times 2 is negative 10. So we're going to keep the negative 5. Now we reduced it by 1 here. If we reduce it by 1 again, we have 1. Negative 5 times 1, negative 5. Perfect. Now let's see if we get a pattern here. We're starting with negative 5 each time. Each time we're reducing what we multiply by 1. We're subtracting 1 from that. Our answer goes from negative 15 up to negative 10. From negative 10 up to negative 5, the answer is increasing by 5 each time. So let's do it again. We keep that at negative 5. What's this have to be? 0. We subtract 1 again, it's 0. Well, what negative 5 times 0 is? 0. Did this go up by 5? It did. So the pattern is continuing. So now we assume, so now we're going to assume that it keeps going. So negative 5 times 1 is, negative 5 times negative 1. This has to go up by 5. It would be positive 5. Negative 5 times negative 2. This would have to go up by 5 to 10. Negative 5 times negative 3. That would have to go up by 5 to 15. So the only reason that a negative times a negative equals a positive is because it continues the pattern. Division goes off of the same pattern. If I have a negative 24 divided by 8, Well, a negative divided by a positive is negative. 24 divided by 8 is 3, so it's a negative 3. If I have 36 divided by a negative 4, well, positive divided by a negative is negative. 36 divided by 4 is 9, so it's negative 9. If I have a negative 42 divided by a negative 7, a negative divided by a negative is positive. 42 divided by 7 is 6. So it's just 6 or positive 6. Okay, we've got 3 minutes to show you just one quick little thing. What's that mean? 8 to the power of 3. Good. And how would we calculate it? 8 times 8 times 8, which is 512. Now for this one, you could probably punch in your calculator 8 times 8 times 8. But what if I had 2 to the 10th? 1,024, but you wouldn't want to be sitting there trying to punch in 2 times 2 times 2, keeping track of, did I hit it 9 times or 10 times? There's a key on most of your calculators that looks like this. It's called the Caret Key. Some of you might have a y to the x or x to the y key. Those are your power keys. You would type in the 2, press whichever key it is that you have, and then type the 10, hit equals, and it'll spit out the 1,024. A word of caution here. Negative 5 squared. Well, what's negative 5 squared? It's negative 5 times negative 5. What's that come out to be? Positive 25. But let me show you something on my calculator. This is the negative key right down here, by the way. Instead of using the subtraction key, use that negative key. I do negative 5x squared. My calculator is going to try to tell me that it's a negative 25. Obviously, that's not right. We know it's a positive 25. Well, on your calculator, you have to put negatives in parentheses when you raise them to a power. Now it'll do it correctly. We haven't talked about order of operations yet. That's where one of the things we'll start with next time. Order of operations, the power would happen before the negative. So you have to use those parentheses to tell the calculator, no, you got to square the negative 5. You're not squaring the 5 and then putting the negative on it. Then, of course, along with that is this symbol. The square root of 36. It's just asking the opposite. It's asking what number squared is 36. That would be 6. And there's also technically negative 6, right? Because negative 6 squared would also be 36. For our purposes, we'll only use the 6, and we just lost our connection. So anyway, homework, I'll give it to you guys here, and they'll have to catch it off the recording. Is the page 7 through 8 listed on the sheet? 1 through 59, the odds. Page 18 through 21, 1 through 97, the odds. Page 29 through 32, 1 through 91, the odds. Now on the homework, I'm not expecting to sit there and pound. I mean, that's like 110 problems there. I'm not expecting you to sit down and pound through that many problems. The homework is there to give you recommended practice so that you're comfortable doing it. If you do the first one and it's really easy, skip ahead a few to the more difficult ones. Make sure you do enough that you know how to do it, but I don't expect you to sit there and do busy work on stuff you already know how to do. Any questions? Okay, well, you guys have a great week, and we'll see you next Friday.